A hypernova is a type of star explosion with an energy substantially higher than that of standard supernovae and is one of the most catastrophic events in the universe. An alternative term for most hypernovae is superluminous supernova. Such explosions are thought to be the origin of long-duration gamma-ray bursts. Just like supernovae in general, hypernovae are produced by several different types of stellar explosion, some well-modeled and observed in recent years, some still tentatively suggested for observed hypernovae, and some entirely theoretical. Numerous hypernovae have been observed corresponding to supernovae type IC and type IIN, and possibly also at least one of type IIb. History of the term. Before the late 1990s, the term hypernova was used sporadically to describe the theoretical extremely energetic explosions of extremely massive population 3 stars. It has also been used to describe other extreme energy events, such as mergers of supermassive black holes. In 1998, a paper suggesting a link between gamma-ray bursts and young massive stars formally proposed to use the term hypernova for the visible afterglow for those gamma-ray bursts. The energy of such events was speculated to be up to several hundred times that of known supernovae. Almost simultaneously, various overluminous supernovae were being discovered and investigated. These events were described as hypernovae and varied from less than 5 to around 50 times as energetic as other supernovae and up to 20 times as luminous as a standard type Iowa supernova at its peak. This definition has become standard for the term hypernova, although not all of them are associated with gamma-ray bursts. The word hypernova itself was coined by S.E. Worsley. Investigation of these types of luminous supernovae suggests that some of them are due to explosions of extremely massive low metallicity stars by the pair instability mechanism, although not with the energies that were speculated for them decades earlier. Gamma-ray bursts. Gamma-ray bursts are some of the most energetic events observed in the universe, but their origin was entirely speculative until around the year 2000. Now, supernova explosions are known to cause at least some gamma-ray bursts, although gamma-ray bursts are also likely from completely different events, and not all supernovae are associated with gamma-ray bursts. A nearby gamma-ray burst could destroy life on Earth. However, no likely candidate progenitors are close enough to be a danger. Some astrophysicists have suggested that a gamma-ray burst may have caused the Ordovician Silurian mass extinction on Earth 440 million years ago, but no categorical evidence for this hypothesis exists. Causes of hypernovae. A wide variety of models have been proposed to explain events an order of magnitude or more greater than standard supernovae. The collapsar and CSM models are widely accepted and a number of events are well observed. Other models are still only tentatively observed or entirely theoretical. Collapsar model. The collapsar model is a type of hypernova that produces a gravitationally collapsed object, or black hole. The word collapsar, short for collapsed star, was formerly used to refer to the end product of stellar gravitational collapse, a stellar mass black hole. The word is now sometimes used to refer to a specific model for the collapse of a fast-rotating star. When core collapse occurs in a star with a core at least around 15 times the Sun's mass, though chemical composition and rotational rate are also significant, the explosion energy is insufficient to expel the outer layers of the star, and it will collapse into a black hole without producing a visible supernova outburst. A star with a core mass slightly below this level, in the range of 5 to 15 m, will undergo a supernova explosion, but so much of the ejected mass falls back onto the core remnant that it still collapses into a black hole. If such a star is rotating slowly, then it will produce a faint supernova, but if the star is rotating quickly enough, then the fall back to the black hole will produce relativistic jets. The energy that these jets transfer into the ejected shell renders the visible outburst substantially more luminous than a standard supernova. The jets also beam high-energy particles and gamma rays directly outward and thereby produce X-ray gamma-ray bursts. The jets can last for several seconds or longer and correspond to long-duration gamma-ray bursts, but they do not appear to explain short-duration gamma-ray bursts. A star with a 5 to 15 m core has an approximate total mass of 25 to 90 m. If the star has not undergone mass loss, such a star will still have a hydrogen envelope and will explode as a Type II supernova. Faint Type II supernovae have been observed, but no definite candidates for a Type II hypernova. Only the very lowest metallicity population 3 stars will reach this stage of their life with little mass loss. Other stars, including most of those visible to us, will have had most of their outer layers blown away by the high luminosity to become a Wolf-Rayet star and will explode as Type IC supernovae. Many observed hypernovae are Type IC, and those associated with gamma-ray bursts are almost all Type IC, and these are very good candidates for having relativistic jets produced by fallback to a black hole. Not all Type IC hypernovae correspond to observed gamma-ray bursts, but the burst would only be visible if one of the jets were aimed towards us. In recent years, a great deal of observational data on long-duration gamma-ray bursts has significantly increased our understanding of these events, and made clear that the collapsor model produces explosions that differ only in detail from more or less ordinary supernovae and have energy ranges from approximately normal to around 100 times larger. Nevertheless, they continue sometimes to be referred to in the literature as hypernovae. A good example of a collapsor hypernova is SN 1998 BW, which was associated with the gamma-ray burst GRB 980,425. It is classified as a Type IC supernova due to its distinctive spectral properties in the radio spectrum, indicating the presence of relativistic matter. CSM model. Almost all observed hypernovae have had spectra similar to either a Type IC or Type IN supernova. The Type IC hypernovae are thought to be produced by jets from fallback to a black hole, but Type IN hypernovae have significantly different light curves and are not associated with gamma-ray bursts. Type IN supernovae are all embedded in a dense nebula probably expelled from the progenitor star itself, and this circumstellar material is thought to be the cause of the extra luminosity. When material expelled in an initial normal supernova explosion meets dense nebular material or dust close to the star, the shockwave converts kinetic energy efficiently into visible radiation. Thus we see an extremely luminous supernova of extended duration even though the initial explosion energy was the same as that of a normal supernova. Although any supernova type could potentially produce a Type IN hypernova, given suitable surrounding CSM, the constraints on the size and density of the CSM mean that it will almost always be produced from the star itself immediately prior to the supernova explosion. Such stars are hypergiants and LBVs undergoing substantial mass loss due to Eddington instability. For example, SN 2005 GL, pair instability supernova. Another type of hypernova is a pair instability supernova, of which SN 2006 GY may possibly be the first observed example. This supernova event was observed in a galaxy about 238 million light-years from Earth. The theoretical basis for pair instability collapse has been known for many decades and was suggested as a dominant source of higher mass elements. In the early universe's supermassive population, 3 stars exploded. In a pair instability supernova, the pair production effect causes a sudden pressure drop in the star's core, leading to a rapid partial collapse. Gravitational potential energy from the collapse causes runaway fusion of the core, which entirely destroys the star, leaving no remnant. Models show that this phenomenon only happens in stars with extreme low metallicity and masses between about 140 and 260 times the Sun, making them extremely unlikely in the local universe. Although originally expected to produce hypernova explosions hundreds of times greater than a supernova, current models predict that they actually produce luminosities ranging from about the same as the normal core collapse supernova to perhaps 50 times brighter, although remaining bright for much longer. Magnetar energy release. Models of the creation and subsequent spin-down of a magnetar yield much higher luminosities than regular supernova events and match the observed properties of at least some hypernovae. In cases where pair instability supernova may not be a good fit for explaining a hypernova, a magnetar explanation is more plausible. Other models. There are still models for hypernova explosions produced from binary systems, white dwarf and neutron stars in unusual arrangements or undergoing mergers, and some of these are proposed to account for some observed gamma-ray bursts.